We've been talking about how this had to do with rate of change. Well, we can use rate of change with different factors. So you have some function here. Draw a tangent line at the indicated point on the function below. So a tangent line, I don't care how you make it, but tangent just touches, so it's not going to actually go through the graph. So maybe something like that. Okay, that might be my tangent line. This graph, let's say, it says suppose it was a profit function. Can we use the tangent line you drew to estimate the profit? Well, if I said that this was, like X is my number of items, and this is my money, okay? So my profit is going to have to do with my amount of money per the change in the items. Does that make sense? Like, however many, if you have a bake sale and it costs $5 for all the ingredients and you buy so much, where's your profit going to be? Well, it's going to have to do with how many items are bought. So if I say at this point, that's my profit when there are X items bought at that point. If I want to find out what happens when you are like out here somewhere, that's going to be my actual change in profit, because that's an actual point on my profit curve. So let's say that that's when you buy just one more item. Okay, so if this distance is 1, when you've bought one more item, then what would this be right here, this value? X plus 1. And this Y value would be P of X plus 1. So what's the change in profit? How would I find this amount right here? The change in profit could be found by doing what with those Y values? Subtracting them. Okay, and that's kind of what it was saying down here. I just didn't refer to it exactly. If I want to find the slope, as long as I didn't go like too far away, as long as I didn't get my points too far apart, then I could look at the slope of that tangent line. Slope of the tangent line is just delta y over delta x. Right? When you find slope, it's delta y over delta x. So if I want the slope of my profit line, remember slope and derivative are the same thing. It's going to be change in y over change in x. Well, my change in y is right now p of x plus 1 minus p of x. And my change of x, well, I just said go 1 unit. But that comes from x plus 1 minus x. Okay, y2 minus y1 over x2 minus x1. That's all I just did. Just didn't label it that way. So the derivative is the change in profit. It's what it is for this graph. Type it in. Okay, consider the tangent line. The slope of the tangent is given by what? The slope of the tangent line, just kind of, I guess, kind of answered that. The slope of the tangent line is this, p of x plus 1, change in y over change of x. So p of x plus 1 minus p of x over your change in x, which is 1. So it's change in y, p of x plus 1 minus p of x over x plus 1 minus x, which is 1. The slope of the line is given by that derivative function. Kind of what I was wanting there. It's just re-saying what I just said, actually. So basically, the underlying principle, this is the underlying principle of the following definition. So if x changes by 1 unit, then the change in y is approximately the value of the derivative at point x. So that's nothing different than what we've been talking about. If you want to find the change in y over the change of x, that's slope, that's first derivative. So that's the underlying principle around marginal cost. I don't know if you've talked about that in Krainer's class yet. But the marginal cost at x given by c prime, so where say c is a cost function. So we're given by the derivative is the approximate cost of the x plus 1 item. So the marginal cost is what happens if you have x items and you get one more. The x plus first. I didn't know how to write that. Marginal revenue. Revenue, let's say that's R. So the derivative of the revenue function. It's the revenue generated by that x plus first item. Profit, the marginal profit is the derivative of the profit function. It's generated by the x plus first item. So let's see what that means kind of in a realistic, hopefully, problem with those definitions. I know. The definitions are kind of gibberish, but basically knowing this part, if I ask for marginal cost, it's the derivative of the cost function. Marginal revenue is the derivative of the revenue function. Marginal profit is the derivative of the profit function.
What's the cost function?
Cost function, they're going to give it to you. So suppose that the daily cost in dollars of producing X radios is C of X equals that crap. And currently there are 40 radios produced daily. What is the current daily cost? How would you figure that out? Not even that. You wouldn't even have to find the derivative. If I just want the cost, and that's the cost function, plug in 40 for X. So do that. Plug in 40 for X. I'm not going to write it all out. You can do that in calculator. What do you get? Okay. Alright. What would the additional daily cost of increasing production to 41 radios daily? What would be the additional, that should say? What would be the additional daily cost? That'd probably make more sense. Of increasing production of 41 radios daily. So what would you do there? Okay, so C of 41 minus C of 40. So change all those 40s to 41s. Then what do you get? So this would be your 2,268. What did you get for 41? $23, $27, $94. So what's that, like $59.94? Okay. So So $59.94 would be the increase in the daily cost. What is the marginal cost of the 41st unit? Well, up above it says marginal cost at X is given by the derivative of the cost function of the X plus first item. So find the derivative of the cost function. What's the derivative going to be? Okay. So what happens when you plug in, the marginal cost is at X. So what happens when you plug in 40 to that?
Why wouldn't you just do 41?
It says that the marginal cost is, the marginal cost is given by C, the derivative of X. Try plugging in 40 and telling me what you get. Let's start there. I should have worked this out better. 59.60. See how that's approximately 59.94? It's another way of doing, basically finding the exact same thing.
Yeah, but you're supposed to find it at the 41st.
You are, but it's by finding the marginal cost of to find the marginal cost of the 41st item, you can find the derivative of the cost function, the change in the cost function at that particular point at 40, which is what it wanted, what the daily cost is, and it'll give you about the same answer is what it's trying to say. It's trying to show you kind of two ways to doing it. You can find the additional cost of increasing production, because that's change. Additional cost would be, what's the change in Y over the change in X? Isn't that slope? The change in Y is 59.94 over the change in X, which you're going from, you're adding one more item. 41 radios instead of 40. Isn't that another word for slope? And derivative is also another word for slope. So if I find the derivative of the cost function at that 40, I should get about the same answer as what I did here. That's what it's trying to point out. So do this one either way, really. We should be able to do it either way. Suppose the cost of producing X units is given by this. What is the marginal cost of producing the 11th unit? So what do you plug in?
10.
If you're going to find the derivative, you plug in 10. So you plug in one less than what you want. So if I find the derivative, what would the derivative be? See, this is 4x squared plus 300x to the negative 1, let's say. So the derivative is okay. So Brooke says if I plug in 10 to that derivative, I should get the right answer. Let's see, 8 times 10 is 80. That'd be 300 over 100, which is 3. She gets 77. It's a different function, so it shouldn't be close to that $60. It's a different function. The marginal cost of producing the 11th unit, if that's the function, is $77. So if I asked for the 50th unit, how'd I get 3? This means 300 times 1/100th, which is 3. Which is what your calculator would do as well. So if it asks for the marginal cost of the, 50th unit, you plug in 49. Plug in one less. Or you can do it like in part B. Take C of 1 minus C of 40. That's Y2 minus Y1 over X2 minus X1, which is 1. So you can do it that way as well. I I could have plugged 11 in and plugged 10 in and subtract them, and I'd get about the same. It'd be a little bit off, but it'd be about the same. Huh? So, yeah, kind of weird. All right, so lesson 8. Did any of you take a look at it last night? Yeah. Let's kind of start doing a couple of them together to get you going. Yeah, we'll just start it. Okay. Did anyone get an answer for number 8?
80,000
80,000?
gallons over a minute, and then the other part. I got 8,000.
Did you get 80,000 over 10 minutes? To give you 8,000? Oh, to give you 8,000? Okay, that is right.
What?
You'd have 80,000 over 10 minutes, which is 8,000.
Like for the first question, how fast is the water running? I got.
At the end of 10, okay,
And then for
I got you.
the average, I got 8,000.
This has 10,000. So let's see. All right, so the number of gallons of water in a tank T minutes after the tank has started to drain is that. How fast is the water running out at the end of 10 minutes? So, 200 times 30 minus T squared. All right, so what did you do first? Huh?
First,
Yeah, what did you do? What did you...
into that equation.
Oh. It wants to know how fast is the water running out. So that's the rate.
Yeah.
So you want to plug 10 into what?
That equation.
No,
Why not?
the derivative. The derivative is the rate of change. So you want to plug 10 into the derivative. Because it's asking the rate of change after the 10 minutes.
How do you know that?
Yes, that's what we talked about yesterday, was rate of change. I would probably go ahead and FOIL this out. And probably even simplify it from there instead of worrying about like the product rule or something. 200 times 900. 180,000 minus 12,000. I believe if I did the math right, 180. Yeah. So your derivative, your rate of change, would be what? Negative 12,000 plus 400t. Now it wants to know the rate of change after 10 minutes. So the rate of change per minute for those 10 minutes. So that's where I'm going to plug in my 10. So negative 12,000 plus 400 times 10 is what? Negative 8,000. So the rate of change is 8,000 gallons per minute. What is the average rate at which the water flows out during the first 10 minutes. So yesterday we talked about how how fast it was going at that 10 minutes, that's like your instantaneous velocity, your instantaneous rate of change. Your average rate of change is over the whole thing. It's the slope of the secant line is what it is. So it's your slope formula, basically. So the average rate of change over that whole 10 minutes, so from 0 to 10 minutes. Well, if at 0, how much at time 0, how much water is leaving? Nothing's really started yet, so how much water is leaving? 0. At 10 minutes, how much water is leaving? That's the, 80,000 that you guys told me a minute ago? Oh, wait a minute. 8, plug in 10. Oh, shoot, wait a minute. Plug in, sorry, hold on. Plug in 0, what do you get? Plug in 0 to the original problem. How much water was in there? Not 0, it was what? 180,000. Okay? So you have a point, at time 0, there's 180,000 gallons of water in the tank. No water's left, so it's completely full. At time t, which is 10 minutes, if I plug in 10, how much water is there? Well, maybe go up here even. Plug it into clear up here if you want. It'll save you some math. 30 minus 10 is 20 squared. 80,000. All right. So your average rate of change then is going to be your slope of this line. So 80,000 minus 180,000 over 10 minus 0. So the average rate at which the water flows out during the first 10 minutes is what? 10,000 gallons per minute. Why wouldn't those two numbers be the same? One's an average, yeah. At the beginning, when you just open up the hole, is it going out quite as fast? No, or whatever it was. Was it a hole? The drain. When you first open up the drain, it's not going out as fast. If you've ever, let the water out of a tub, at the end it doesn't start running out. It's not running out quite as fast because there's not as much water left in there. You're trying to push all the water down to the end to get it to go out. What's that idea? Let's go ahead and do number 9. The accompanying figure shows the velocity v equals f of t, so that's the velocity function, of a particle moving on a coordinate line. When does the particle move forward? This is what we talked about yesterday. It's pretty much this, it's a very similar graph. When does the particle move forward? 0 to 1 and 5 to 7. All right. So yep.
Why are they bracketed?
Tell me.
The other one that we did yesterday.
Yeah, it starts up at 5. Yeah, it doesn't start right at 0.
So 0 would be a bracket.
Yes.
9 would be a bracket.
0 in the right now, just the 0.
But if you have 9 in the answer, it would be
I don't think so because you're at 0. You're not starting up in the air. Because remember, there isn't any velocity where it hits the x-axis. That's where the velocity doesn't exist. When is the particle? When does it move backwards? This is the next question. What? 1 to 5. Okay. This is forward, this is backward. Okay. When does it speed up? 1 to 2 and 5 to 6. Okay, and how did we figure that out yesterday when that happens? Okay, so when the velocity and the slope are the same sign. Exactly what you said. When is it slowing down? From where to where? 0 to 1, 3 to 5, and 6 to 7. 0 to 1, 3 to 5, and 6 to 7. Is that what you said? 0 to 1, 3 to 5. Okay, so 0 to 1 and 6 to 7, in both of those instances, it's sloped downward. And it's above the x-axis. And then the 3 to 5, it's sloped upwards, and it's below the x-axis. So again, that's the idea of when you have the same sign. B. When is the particle's acceleration positive? 3 and 6. When is the particle's acceleration positive, negative, and 0? Okay. So from, what did you say, positive from where to where? 3 to 6. Okay. So from 3 to 6, if I was to take the derivative of this function, because that's what acceleration is, the derivative is the slope. So if I look at the slope of that graph, it's positive from 3 to 6. So that's when the acceleration is positive. When is the acceleration negative? Zero to 2, it's sloped downwards, and 6 to 7, exactly right. When is the acceleration 0? Or constant? So when the slope is 0 of a constant function. Right. Zero to 3 and 7 to, or 2 to 3 and 7 to 9, because that's where it stops. You can have the closed here. Oh, and I stopped going brackets, sorry, but you know what to do on there. When does the particle move at its greatest speed? So when the velocity is at its greatest, it's when the velocity is maximized. So you said 0 and then where? 2 to 3? Okay. Okay. When does the particle stand still for more than an instant? There's 2 spots. 2 to 3. And 7 to 9. I lost my graph. 2 to 3, 7 to 9. Alright. And actually, they didn't have the 2 to 3. I don't know. They must be counting an instant as more than a second, but to me, it works. All right. 13 through 16 are kind of similar problems. Did you guys look at 13?
Yeah, and I knew how to do it.
Okay. So a rock thrown vertically upward from the surface of the moon, a rock thrown at a velocity of 24 meters per second reaches a height of s equals 24t minus 0.8 t squared meters in t seconds. Find the rock's velocity and acceleration as functions of time. So they're giving you the displacement function, the s function. How do you find the velocity? Yeah, you take the derivative of what they're giving you. So, let's see. So the velocity is 24 minus 1.6 t, right? Meters per second. And the acceleration is negative 1.6 meters per second squared. All right. So you do the derivative again, yep, of the velocity. Okay. So B, when does the rock reach its how long did it take the rock to reach its highest point? So it's going to reach its highest point when your velocity is 0, when it stops. If I throw a ball up or a rock up or whatever, at some point it's got to stop and come back down, right? Stop just instantaneously, just for a single instant. When it stops, that's when it's reached its highest point, when its velocity is 0. So I'm going to take my velocity graph, or equation in this case, 0 equals 24 minus 1.6 t. I'm going to solve that. And what is that? 38.4? Okay. Wait, no, what? 24 divided by 1.6? Should be like 15 something, I think. All right, 15 seconds. All right, so C, how high did the rock go? Well, if that's how long it took it to reach its highest height, how would you figure out how high it went? What would you do with that answer? Plug it into the original. Plug it into that position function, that 24t minus 0.8 t squared. So 24 times 15 minus 0.8 times 15 squared. Did you do a minus here or did you do a plus? Yeah, I think it should be 180 meters. So D, when did the rock reach half its maximum height?
Teachers, I'm sorry for the interruption. I do have a couple of announcements. Seniors, I do want to remind you that we have Army and college visits signed up in the counselor's office. So sign up in there. The Army will be here tomorrow if you are interested in meeting with them. And for tonight, girls open gym for this evening has been canceled. Boys basketball open gym will be moved from tomorrow night to tonight from 7 to 8:30. So no open gym tomorrow. Tomorrow is Titan Spirit Day. Our girls volleyball team will be playing Limestone for the regional title at 6 p.m. tomorrow night. Both the girls and guys cross-country teams will be running at sectionals in Elmwood on Saturday, beginning at 10:30 a.m. Let's show our teams how proud we are and wear our Titan colors tomorrow. Also, a reminder that Friday is Halloween. Donate $1 to wear a Halloween costume, and this must follow dress code rules, or you can even wear your school spirit again. Go Titans, go cheer everybody on. Thank you, have a great night.
So, for D, you want to find out when it's reached half its maximum height, which would be a height of what? 90. So you're going to take that position function, that 24t minus 0.8t squared equals 90, and solve it. You might have to do quadratic formula. I don't think it factors. So then E, how long is the rock aloft? We did this yesterday. How long was the rock in the air? Well, when it falls, what's its position going to be? 0. So take that position function, that 24t minus 0.8t squared, and set it equal to 0 and solve it. (14) and 15 and 16, I think you will find will ask similar questions to what we just did. I mean, I think you'll be able to use that to help you. 19 through 24. 19 is pretty similar in a way. 27, 28, and it has to do with what we talked about with the notes today.